ไปนะคะวิทยากรท่านแรกค่ะจะมาบรรยายให้ทุกท่านรู้จักกับเทคโนโลยี Microgroove ท่านเป็นโปรแกรม Director ของสถาบันทองแดงยุโรปหรือ ECI นะคะและยังเป็นหัวหน้าทีม Microgroove ระดับนานาชาติของ ICA อีกด้วยค่ะขอเรียนเชิญ Mr. Nigel คอตตันค่ะ Please Mr. Nigel
Good morning, everyone. I'm very pleased to be here today with you in Bangkok. Today, we will examine trends in heat exchange design and understand what is driving these changes and the available technology. We will look at the basic technology behind heat transfer and the benefits of small diameter copper tubes, and the focus will be on increasing energy efficiency using eco-friendly refrigerants. We've set up a Microgroove.net website where you'll find member companies of the ICA who produce copper tubes and can provide more information about specific tube products and supply chain solutions. These companies are listed on the suppliers page of the Microgroove.net, as well as information about up-and-coming events, news, releases, and our Microgroove Update Network newsletter. Our coils today are made with round tube copper tubes laced into plate fins. The fins are usually made of aluminium, but could also be made of copper if you want the antimicrobial properties. A vital step in the manufacturing process is the expansion of copper tubes so they make good thermal contact with the fins and so allow for efficient heat conduction. The resulting heat exchangers are used in a variety of applications in residential, commercial, and industrial settings. Specifically, reducing the diameter of copper tubes can improve heat transfer and result in more energy efficient, smaller, and lighter coils, bringing about all those benefits to manufacturers, distributors, and end users of air conditioning and refrigeration systems. These benefits are associated not only with meeting energy efficiency and low global warming potential refrigerant regulations, but also with a reduction in material usage and system costs. All of these benefits contribute towards sustainability and global competitiveness. Round tube plate fin coil has been used for many years, probably for nearly 100 years. Tubes with internal grooves and enhancement were developed in the 1980s. These internal modifications greatly improved efficiency and quickly became the market norm. The name Microgroove today refers to these internal enhancements as well as smaller diameter tubes. There are a number of factors behind the move towards small diameter tube. They range from government mandates on energy efficiency, such as increased seasonal energy efficiency ratings, to the phasing out of high ozone depletion refrigerants, to the high pressures associated with new refrigerants or natural refrigerants. The drive to these increase the coefficient of performance is another factor behind the trend towards small diameter tubes. The design of ACR coils is a complicated subject. These processes can be modeled through computer simulations which can predict the performance of such systems. Kerry and the Shanghai University will present more of these details on computer simulation later in today's agenda. The slide here shows the basic circuit for heat exchange systems. In many cases, the highest thermal resistance is due to the local heat transfer coefficient. What is actually happening is inside the tube between the refrigerant and the tube wall, and this often sets the limit on the system efficiency. Focusing on the local heat transfer coefficients, the fluid closest to the tube wall sets up a boundary layer where heat transfer becomes more difficult. In simple terms, the boundary layer acts as an insulator and interferes with the heat transfer. The internal enhancements reduce the boundary layer and thereby increase the heat transfer coefficient through the tube wall. The boundary layer in the smooth tube is compared to the boundary layer in the tube with the microgroove enhancement. The additional mixing of the refrigerant that occurs inside the tube, because of these grooves, increases the amount of refrigerant that comes in contact with the tube wall. When this advantage is combined with small diameter tubes, there are many more additional advantages. These developments are backed up by experimental and field performance data. The data clearly shows significant advantages to internal enhancement with smaller diameter tubes. As the air flows around the tubes, heat is transferred into the air. Airflow through the coil is affected by the number of tubes, the size, location of the tubes, and the types of fin. The slots and louvers on the fins break up the air boundary layers and improve heat transfer. The International Copper Institute sponsored research at Shanghai Jiao Tong University and the Center of Environmental Energy Engineering at the University of Maryland to develop correlations for tube and fin designs for use in the microgroove technology. Correlations for slotted fins and louvered fins were recently presented at the 2016 Purdue Conference in America. Smaller diameter tubes with thinner walls can hold the same pressure as larger diameter tubes. So reducing the diameters actually reduce the weight of the materials being used and in turn reduce costs. As the tube diameter is further decreased, surface area is gained in relation to the volume of the refrigerant in the tube for the same amount of material. Furthermore, tube wall thicknesses can be reduced and still meet the pressure criteria for larger tubes, or higher pressures can be tolerated in smaller diameter tubes with the same wall thickness. In other words, we can do more with less material. Now let's talk about manufacturing of coils with small diameter microgroove tubes. This topic will be covered in greater detail later today, but considering the importance of manufacturing on the final cost and practicality of coil designs, here is an overview. As you can see, there are many things that you use as determinants as to which parameter you wish to change. Reducing the diameter of the tube gives greater design choices. For any given constraint, a design option is available. Coil manufacturing is well known, and the techniques are familiar with the industry. Fin spacing is maintained by the size of the collar that is formed around the holes for the tube. Fins can be stacked prior to the lacing. The tubes are then expanded in diameter, and this binds them to the fins mechanically and ensure proven heat transfer. The U-shaped fitting are brazed onto the tube ends, and this determines the exact circuit that the refrigerant will travel through the coil. This is a well-established process, it's very reproducible and very robust. This method of manufacturing coils continues to set the industry standard for corrosion resistance and reliable surface life. Since this process remains largely unchanged for small diameter microgroove tubes, engineers and technicians throughout the industry are familiar with the practices and also the costs associated with it. A big advantage of microgroove tubes is the lower refrigerant charge. Aluminium microchannel tubes are joined at the manifold header, and that can take a considerable amount of refrigerant to fill. The circuitry of the copper tubes is much more flexible and can be optimized to minimize pressure drop and avoid the maldistribution problems associated with microchannel heat exchangers. Another problem that's circumvented by the microgroove is the issue of drainage. As you can see here, the open structure of the microgroove heat exchanger allows for easy drainage compared to equivalent microchannel design. This is especially important for heat pump applications involving outdoor evaporators. In conclusion, small diameter tubes allow for energy efficiency designs using less tube and fin material as well as less refrigerant volume. Round tube plate fin heat exchangers are proven, durable products with a history of success behind them. Small diameter copper tubes give engineers the flexibility to design for a wide variety of operating conditions. As will be discovered later today in great detail by other speakers, the manufacturing process is proven, economical, robust, and supported by a supply chain that is well established with manufacturing and distribution systems around the world. Comparison with aluminium microchannel and 9mm copper tube is no longer relevant, as the small diameter tube is the new standard we use today. If you'd like some more information, you can visit our website, microgroove.net. And lastly, I'd just like to thank you for your attention and hope that you enjoy the rest of the day. Thank you.